Here I have a code that's going to show us the effects of gravity that are given to both the planet Kokomo as well as the asteroid that's flying over the top of it, because they're both being affected by the force. So to start off this program, I gave 5 constants. I gave the radius of Kokomo, the planet, the mass of Kokomo, the planet, and the constant g for gravity, which we're going to be using later. I gave the radius for the asteroid, and I gave the mass for the asteroid. Here, Kokomo is a sphere, and I gave it its position vector to be 0, 0, 0, so it's starting at the origin of this simulation. The radius is RK, one of our givens that we have above, so I just plug that in right here. Chose the color to be orange. And the asteroid has a position vector that is only in the y direction, because I want it to be directly above my planet whenever I start the simulation. And its radius is one of the constants right here, the radius of the asteroid, RA. And I gave it a color, green. I like green. And then the Kokomo. The Kokomo momentum is going to equal the mass of the Kokomo times its velocity, which is velocity in this case is 0, 0, because I want it to be at rest at the start of this reaction, at the start of this interaction between the asteroid and Kokomo. For the asteroid, I have the momentum equal to its mass, the constant given above, times its vector of a x velocity and no y nor z velocity yet. I have my initial time period, and I have my change of time period that I'm going to use in my loop. In my loop, I have a cutoff point, a time, that period that I want the loop to last for. I want it to last for 10 to the 9th power seconds. And then I have it at a rate of 100. Let's see. So here I have the position. I have the position vector of Kokomo and the position vector of the asteroid, and these two are in my loop so that I can calculate the distance between the asteroid and the Kokomo, because in the whole time of this loop of this program, we're going to be seeing this distance r between the center of the asteroid and the center of Kokomo is going to be changing as it is orbiting around, as the asteroid is orbiting around Kokomo. So I gave it r hat to be equal to norm r, which is the same thing as r hat. I just did this so it would be easier to plug in r hat into my equation for the force of gravity. And I said that the force of the gravity on the asteroid applied by Kokomo is going to be constant g given above times the mass of Kokomo, which is also given above, and the mass of the asteroid, which is given above, times r hat, which I have here. And then I want that all to be divided by the magnitude of r squared, which I'm going to get my r from this part of the code right here. And so I have my asteroid's momentum being updated in the loop, as well as my asteroid's position. And I had the same thing for my planet, Kokomo. The asteroid's momentum is going to equal the asteroid's initial momentum plus the force of gravity affecting it over a change of time. This is the basic momentum principle formula. We have our final momentum is going to be equal to our initial momentum plus the net force of gravity times the change in time. So that's that. Same thing below for Kokomo. And my position vector is going to be equal to the initial position, asteroid position, plus the asteroid's position times the change in time divided by the mass of that object. It's going to give me the momentum divided by the mass. It's going to give me the velocity. That way I can calculate the velocity times the time to figure out how much distance was traveled in that period of time of dt. And there you have it. When I click it, it doesn't run, but I'm working on that. So